Oh shit. It's tutorial time! Hello. Today we're going to be doing linked list, stack, and queue. Now, I know that everybody's kind of seen the linked list before a little bit in lectures. Sorry about the delay here with the tutorial. It's assignment 1 specials kind of took over last week, so these are pushed back a little bit. But stack and queue are also going to be covered today. And I've also prepared a little animation that's going to help explain maybe how the linked lists work and like what they do. And you might have seen that on my courses as well, but I'll play it during this session in addition. So first off, we'll just hit the slides right away, and I'll go through what we're going to be doing today. Let's just get to the first slide, shall we? Yeah, bam. So today what we'll be doing mostly is we're writing a basic linked list very quickly. We'll just write the most simple, minimal, like easy linked list for those who don't know what the heck we're talking about. Then we're going to upgrade it to a doubly linked list. We're going to upgrade it to a generic list. And I don't know if you guys have seen generics before, but we're going to cover generics. Then we're going to go into stack and a queue. We're going to explain what a stack and queue is, how it's different from a linked list, and then we're going to apply all this to the snake game that we made before. So, quick overview of a linked list. Linked list is this sort of data structure which is built on nodes, and a node holds a payload, which is some object, and also a pointer to another node. And that way we can add on very easily because we can just change the pointer of a node, and that will add on or stitch lists together and everything. And a linked list object just holds a head and sometimes a size and sometimes a tail. So that's generally the idea of a linked list. And then behind my overlay here, we have a very insightful meme that might help our understanding of it. So without further ado, I'll get into our little animated explanation. Then I'll take any questions about the theory on linked lists, and then we can get straight to the implementation, and we'll try to speed through it as much as possible so that we can get to the new stuff, stack and queue, in a timely manner. Let's take a moment to consider how our computer stores variables in memory. We can imagine our memory as a continuous line of slots, each with their own associated number, indicating which slot it is. And in this, we can store our primitives. We can consider another area of our memory to store references, which we'll call the stack and the heap. This is not the full idea of stack and heap. That's a rather complicated concept. We'll do a simplified version for this tutorial, where we will think of it as values and references. Our references can point to a value, and that value can change. It's mutable, and the reference will stay the same. We can also reference multiple values from one reference, and that's called an array. When we create an array, we allocate a certain number of slots from values to a certain reference. Here, we allocate 8 slots to a reference called array of int. And in those slots, we fill it with ints. The blue array, we will call it, starts at index 1. And when we want to resize it, we have to create a new array, starting at a new memory area, and we have to fill it by copying the values from the first array. This is a time-consuming and tedious process, and we have 2 arrays existing in the memory at the same time. When we want to swap it over and make the previous array into the new array, we don't actually change the array. We rather just change the reference. We change the blue array to be pointing to the newly created array, and then we can discard the red array as it no longer exists. It's pointing to the same thing. Now garbage collection will take care of the old values that we've already copied over and are no longer being referenced by anything, and we have a resized array. But notice that we created a whole new array in memory. It has nothing to do with the original array we created. We copied over all the values, added our new value, changed the size, and then changed the reference. We didn't actually resize the original array. To have a resizable data type, we have to consider something a little bit differently. And for that, we're not going to think about our memory anymore in values and references. Rather, let's just think about memory as storing objects. We have a certain amount of slots which can be occupied by any kind of object that is defined in a .java file. Objects can contain whatever fields we want, primitives, or references to other objects. Here, we will consider an object which is able to reference another object from itself. So how can we do that? Well, what if we had an object which actually references another object of the same type, and then we just have a chain of these references which lead us to the next value? Remember, in memory, we don't know what we're looking at unless we have a reference. So let's say we have a reference to a node at 56. Node at 56 stores a reference to another node at 57 and a value. And that reference is key, because that reference points us to the next node in the list. As we travel through our list, we can see that the existence of the pointer reveals to us the next nodes. And as we follow through our list, and we take our time to iterate through and access each node, noting that it actually takes a long time to traverse through this list. So the more nodes we have, the longer it'll take to get to the last one. We can see that each node indeed has its own pointer and value. And as we follow through, as we cascade down the list through the pointers, we can see what happens when we reach the end of our list. At the end of our list, the last node will point to null, because there is no next element. And this is one of the keys of the linked list. It's easy to add a node. All we have to do is change that null to a new reference, and suddenly, we're able to be transported to our next node, as if it was in the list the entire time. This creation of new references and change of references is the core resizability and modifiability of a linked list. It's what gives it its advantage over an array. So now if we follow through our list, we can see our previous nodes were unchanged from this operation. And as we flow through our memory to get to the next node, we can see that the creation of the new pointer has revealed to us that our list is expanded by 1. And now if we check the value and the reference of this node, we can see that since it points to null, it's at the end of our list. And now we've got a linked list that's modified. This is the core useful feature of a linked list and why we create them, and its advantage over an array. Alright, so that should have hopefully made the concepts of what the linked list and everything is a little bit more clear. And if there are any conceptual questions, those are welcome. And now we should be able to transition over into our implementations. So let's just get over onto that. I'll be using the Snake project from a couple tutorials ago for this, because later on we're going to be using the linked list stack and queue for the Snake game. So first thing I'm going to do is the basic linked list. That's the simple, singly linked list like this. This slide should give us the different types of linked lists and basically how they work. So singly linked list is just a linked list where each node has one reference. That's the first one we're going to be implementing. Then we're going to update it to a doubly linked list, which has here pointers going from each node to the next and to the previous. So that's just a little bit spicier. Then we're going to see stack and queue. Now stack and queue are different based on where they remove and add. So if you see the green add here at the bottom, that green add right there, that means that that's where on the list we're going to add stuff. And up there, there is the minus, the red minus. That's where we remove stuff from that data structure. So in our stack and queue, our stack will add and remove from the same end, and our queue will remove from the opposite end where it adds from. That's the difference, and we'll get into that later in implementation. But first, let's just get our simple, very basic, not very good linked list out of the way. Let's make a really bad linked list. So to start, I'm going to make the class, and then I'm going to ask for you guys' input on how we should do it. So let's call it list of links, perhaps. Okay, so here I've got a list of links class. Now, when I make a linked list, what's the first thing that I should be doing? Like or I guess not the first thing, but what is one of the things that is required by a linked list? This should be sort of review from the last few lectures, quizzes, all this. What are like the essential components?
Heat.
Yeah. So we wanted to have a head. Right? So we'll say
head. Sorry.
Yeah, we wanted to have that, but first we need a class for that. So I'm going to make a class, and we can have classes inside of other classes, and in fact I'll make this a private class. Now what this means is that this class is not going to be accessible from outside. It's just going to be for use inside of list of links, right? Because our list nodes are not useful outside of the linked list. Our list nodes are only useful in the list. So here I'm going to have let's make it a list of strings, right? So private, or we'll just call it public string payload, and public node next. Right? So this node next, what does this mean? Well, node next actually points to another instance of the class node, and this is how our linked list works. So like this is the core of how a linked list works. The reference to next. That's very important. And we have to really understand what it means to have a reference to another node. So if there's any questions regarding that, or like the concept around that, now is a good time to ask. I know it looks a little bit weird inside of the code to have a class called node, which like stores itself. I know that seems really weird, and I can understand if you guys are confused by that. But hopefully it'll make sense through our implementation. In our list of links class, we'll have a private node head, right? And that's technically all we need for a very simple linked list. So I'm going to go pretty fast with these. I'm going to say public list of links, list, not list. I don't want to import that. I just want a public list of links constructor, and it's going to say head is null, null. And that's it. Now, we might also want to keep track of our size, right? And the reason we want to keep track of our size is, although we could count our nodes by iterating through, we might just want to store a size variable and increment it and decrement it. So if we have a size, I'll put it for now. So size equals 0. But for now, we don't actually need it. Like, we can do a lot of things without tracking the size. Now, how could I add something to our linked list? Does anybody have an idea of how an add method would work? Public void add. Well, add methods in linked list work by attaching another node, basically stitching a node onto the end, or by replacing the head. But here, here why don't we do it via head replacement? So if head is null, we're gonna have several cases, right? So if the head is null, we have a case. Now else. So two cases for adding, right? If the head is null and if the head is not null. If the head is null, it's really simple. We just say head equals new node, and we don't have a constructor yet for our node. So let's just generate that. So generate constructor with payload string, okay. And now we're gonna say s, right? So this is just gonna change our head to be the new node, change head to be the new node. Right? And now else, if the head is not null and there's lots of stuff in our list, then what we have to do is we have to say, for example, node new is node added is equal to new node s. Okay, so this is creating a new node, and then we can say added dot next is equal to head dot next, or is equal to head. Head is equal to added. Now what this should do is it should say that the pointer that comes after added will be the head, and the new head is going to be added. So this is going to basically restore our linked list and put this at the new front of our list. Now, with these basic methods, we should actually be able to have a functional linked list. So this right now is a working linked list. Right? It doesn't have remove, it just has add, but it is actually functional, and we can test that if we if we write a main method here. Public static void main string args. And it's a good idea to always test your code as you write it, so that's what I'm doing here. I'm going to say list of links L is equal to new list of links, and now L.add hello, L.add world, L.add it's a me. Alright, now let's see if it works. How do we see if it works? We can use a debugger. I'm going to put the debugger on this line. Click debug. And we've seen that. You can see last week's tutorial if you want to learn a lot about debugging and how the debugger works in general. And is my webcam feed frozen? No, that's great. But yeah, so here we've got our list of links. We can go through. We can watch it add. Now if we look at our list, head, next, next. Well, next is null right now, but now we add it. So now we can see that we have an actual functional linked list. And the way it looks in memory is we have the head, which says it's me, world, hello. Now it added backwards, right? Because we basically shift our list over every time we add. And I do want to have my webcam for that, so I'm going to go unfreeze it really quick. Face cam, settings, deactivate. Okay, now it is unfrozen. And we can go back to it. Okay, so we basically add to the start, right? And then we shift our elements over after we added. So that's why it's going to be kind of backwards. Does it make sense to everybody how all of these work and what's happened here and how this very simple linked list works? Are there any questions about simple linked list operation?
Yes, actually, just a simple question. How many objects do you have at the moment in
Well,
memory?
sure, let's count them. I know this is a very common quiz question, so it is important to think about it. First off, we have strings, right? So this is an object right here, hello. So one, two, three strings. We have one list of links, that's 4. Then inside of the list of links, we have head, 2, 3. So what does that come to, like 7? Um, because we have only a head. Remember that depending on how we do our linked list, we can have a different number of objects. If we have a capital I integer, that's another one. If we have a tail, that's another one. But right now, since we just have head, one object is list of links. One object is our node. Well, this one temporarily exists, but one object is our node head. And then another object is the next 2 nodes. And then we also have in our main method the object hello, the object world, the object it's a me, our args array, and the list of links object. Does that make sense? You can just count them kind of visually here because we have the debugger open. But in general, the number of objects in your linked list depends on if it has a head and a tail or just a head. This very minimum linked list has only the head, the nodes it comprises of, and its like container object, the list of links. In fact, actually, here, I'll give you another useful thing. So the number of objects in this structure, so it's going to be head plus, it's going to be, we don't have a dummy head, so it's going to be head plus all other nodes. Okay, so plus each payload plus one list of links. Can you go over added.next equals head and head equals added quickly again? Yeah, sure. So what does this code do? Let's actually put the debugger on it and let's watch it run, and that should help us really understand what it does, and I'll explain it as well with words, but I think the debugger can also help us here. So the first situation right now, we have a list of links which has a head, and the next pointer is null. What is it doing? It's creating a new node called added. So now in our memory, we have a node called added, right? Added has a payload of world and a next of null. We can see here added.next is null and head.next is null. Well, what happens here? I say added.next equals head. Now, added, let's look at added. Where is it? Here. So added is actually our good list right now. So added has hello and added has world. So added is a good list. Now what we're doing when we say head equals added is we're saying that head, which is stored here, like the head field, is going to be replaced with added. So our list is going to become this one. Does it make sense here? We're swapping the references. We're creating basically the list we want is going to be inside of added. It's like when, you know in an array list, when we copy all the items over and we have this new array and we replace our inside array with the new one. This is the same thing. So this step is kind of equivalent. This is kind of like when in an array list, we replace our array with the new bigger one. Does that make sense? All right, perfect. So now we have this linked list, right? And we can add stuff to it, but I feel like there could be an inefficiency. Could somebody tell me here what operations are going to be slow? And maybe I'll write the size method while you think about it, and that could also maybe shed some light on it. So public int size, while, oh yes, node iterator is equal to head. So while iterator dot next is not null. And now here I forgot to do a size, so int size equals 0. Iterator equals head. If head dot next is null, or if head equals null, return 0. Now here it's going to say while the iterator next is not null, size plus plus, and return size. Right? So could somebody tell me what could be inefficient about this? What could make this linked list faster? Right? If I now system.println l.size, what does it have to do? So if I'm trying to print out the size, what is the operation that it has to do? What takes a long time? This is more a question about time complexity, and you're going to see this in assignment 2 later on. So when it finds the size, it might take a long time, right? So what's going to happen here? how is this size going to calculate? How long is it going to take? Kind of what's up with it? And why isn't it even calculating a size? Is it just running forever? Well, if head is null, if iterator.next. Oh, yeah, I forgot to say size plus plus, and then iterator equals iterator.next. Okay, sorry, that was a mistake of mine. Forgot to actually move it along. So now our size should be 3. No, it's 2. What did I forget? Oh, yeah. I want to also account for the head, so I'll say size equals 1. Because, again, we're assuming our head is not null. So now we will go through. We have a good size reader. If we have nothing in our list, it should read 0. But is there anything slow about this? What can we say about the time complexity of this method? All right, 0. 1. Looks like our size is reading properly, but can we say anything about its time complexity? How do we determine the time complexity of a method? Well, when it comes to time complexity, we don't want loops, right? We don't want to care how long our list is when we do stuff. Can somebody tell me what they think the big O notation, like the runtime complexity of size right now is, considering that we have to go through each node and count them? So we iterate size for every single node in the list. We can watch it run, but could somebody give a guess as to the big O notation time complexity of size? So it's going through every node in the list and adding 1 to the size. O of n. Could you maybe hop on the mic and explain why this is O of n method?
Well, because you have to check every element, so where n is the number of elements, then it would be O of n.
Yeah, that's exactly right. So this is O of n. Is there some way that we could improve that? Is there some way we can improve our size check to be O of 1? Why do we want to improve our size check to be O of 1? Well, let me show you why. What if we want to do this? We want to say while list dot, or I guess while L, or maybe for int I equals L is less than L dot size, L plus plus, or even more, what we might want to do is we want to say while L dot size is not 0, right? So we're going to call this method a lot. So this happens a lot, right? So we really care that our size method is fast because we don't want it to take O of n every time we ask for the size. Well, what can we do? We can add a size counter, right? And if we basically count the size when we add stuff rather than counting the size when we loop through it, it'll be much faster. Let's say private int size, right? Now here we can say size equals 0 in our constructor. And when we add something, we can also say size plus plus. Now, here we are actually still counting the size, right? Every time we add something, we return, or we count the size. But you know what's better about this? It's that every time we call the size method, it's O of 1, right? Because it just has to read this number. So instead of doing a count of every single node every time we ask for the size, we count the size every time we change the list. And then we return the size that we have remembered. So could somebody tell me, what is the big advantage of this method? Why do we keep the size variable here? Well, why is it useful to us to not have to do this? Why is it useful for us for the size method to be O of 1? Well, when we loop through our list, we want a loop that looks like this to not take a really long time. Because if this step is O of n, we're going to have something that goes O of n, and let's say we remove an element every time. It's just going to gradually go through and pop through the list. Then this is going to take absolutely forever, right? And that's not good. So that's why we want our size to be fast. And we only count when we change our list. So we only count nodes when the count changes. Better. Okay, so that's our first kind of upgrade to our linked list. Right now we've got a linked list which also has its size variable tracked. And hold on, my thing isn't even updated. There we go. So now we can add a couple of important methods to our list, like removes. Removes are important because we want to be able to remove an item. And first, I'm going to add a method that will remove just the node that's in the head. So public void. Well, I guess we forgot to have a get method as well. So let's just do get first. Public string get, and I'm going to say get first, right? So get first, and this is just going to return whatever is in the head. So return head dot payload. Then we can have another one. We'll have public string get, and this one will get at an int I. So how could we make a method that will get an arbitrary node? It'll go through our list and it'll find a node at a given index. What does this have to do, and what will its time complexity be? Well, to get at an index from a list, right, we have to actually iterate through our list. So we have to get through I elements. So what here would be our time complexity for get? Or what do we expect? Maybe I'll start writing it out, and you guys can think about time complexity. Or if you want to answer it earlier, you're welcome to hop on the mic. But as soon as you got it, or as soon as you think you got it, let me know. And in the meantime, maybe I'll start writing our method. So while, or first I'll check if the size is too big, right? So if I is greater than size, return null. Or I guess if I is greater than size, or if 0 is bigger than I, return null. Else. Now we can say while int counter is less than I. So counter equals 0, while counter is less than I. Node cur equals head, and we'll say cur dot I plus plus, or counter plus plus. Cur is equal to head dot, or is cur dot next. So we're going to keep going through our list, right, until we get to the ith node, and then we're going to say return cur dot payload. So does everybody understand how this method works? So what's going on right here? Okay, so yeah, this method is iterating through our list and it's getting the thing from int I. So if I type system out println l dot get at 0, system dot out dot println l dot get at 2, we should see hello and it's a me. Let's see. Yeah, it's a me hello, right? So we can get from our list. But what's our time complexity here? Now, this time complexity thing is important. It's going to be big on our quizzes. It's going to be big on our assignments. So it's important that we understand how to see the time complexity with kind of just by looking. And here we can see that the time complexity should be O of what? Is it O of 1? Do we just get it instantly? Oh yeah, O of I, says Aslan. And that's very good. It is actually O of I. Because here, our int I is going to be how many times we're going to go through our items. Basically, one way we can figure out a time complexity is count how many times that we have to say dot next. The amount of times we have to say dot next will be our kind of time complexity. And here we have to say dot next I times. COVID. All right, so since we have to say dot next I times, it will go through the list for O of I. Now, what else can we do here? Well, we have our get method for int I. We have our get first. Now, get first is O of what? Now, get first just gets the payload from the head, right? It's pretty quick. So what would its time complexity be? O of 1. Yeah, that's right. So it just has a 1 time complexity because it just gets a thing very simply. It doesn't have to do any iteration. And now, we actually have almost enough to make a queue. The only thing we need now is our remove method. So let's say public void remove, and we're going to say remove first as well for our first one. And to remove the first thing, we're just going to say, let's say node temp equal to head.next. Head.next is equal to null. Head is equal to temp. Right, so what does this do? It says our nodes are basically being shifted over. Let's see. What I'm going to do is I'm going to say if head is not null. And if the head is null, then it's not going to do anything. Right, so now what we can do is we can actually say this. We can say for int I equals 0, I is less than L dot size, I plus plus, system dot out dot println L dot get I. Now we can L dot remove first. Well, I guess we'll print first and then remove first. We'll say L dot gets and remove first. Dot size. Now we'll say num and L dot get I will be replaced with 0. So now we can kind of go through, right? We can kind of go through our list and we can pop through it, if you will. We can well, what's going on here? So L dot get 0, remove first. Well, maybe we should just say get first. Print line 0, 2, and then we say it's a me hello world. So what's going on here? Could somebody tell me what this might look like what we're doing here? We're getting something and then we're removing that same thing, and we're just getting it and removing it. Does it look like something we've seen before? Kind of going through our list in a way that we're just getting rid of things. Like, let's say if my list was like this pile, we can go through it and just get rid of things, and we access them as we get rid of them. Does that look like any sort of operation we're familiar with? Well, what we're really doing here when we say we're going to remove the first element and return the first element is we're kind of accessing it like a stack, right? Like if we have this stack and we're accessing something, we're taking a look at whatever's on the top and then we're getting rid of it because we're done with it. And then we're looking at whatever's on the top and we're done with it. Thinking about when you're washing dishes, right? So when you're washing dishes, you take whatever's on the top, you wash it, you put it in the clean pile, and then you move on to the next one, right? So does everybody see how like the stack analogy is working here and where this linked list can kind of be used as a stack? So again, all a stack does is remove first and get first. Now I can actually go into the slides here and show you guys some stack methods. Here are the differences basically between stack queue and linked list. So the stack has a push method which will add an element to the list. So what does pushing to the stack do? Well, when you push to the stack, you take an element and you put it on the stack, right? When you pop from the stack, you take an element, you take that same element back off the stack. When you peek, you just take a look at the element and then you put it back. When you pop, you take a look at the element, then you throw it away. So that is sort of the stack and queue method list. So a stack and a queue are actually incredibly easy to write. They are some of the easiest classes you will ever have to write in Java, and I'm going to write the stack right now, and we're going to get to the queue in a second. We're going to have to upgrade our linked list before we can make a queue, but we can make a stack right now. So our public class stack is here, and in our stack we can just say extends list of links, and now we can make our methods, right? What we need is public void push. And now again, push just adds to the stack, so we can say add s, and push has to also take a string, so string s. Now we're going to say public string peek, and that'll just return get first. And public string pop. And now pop is going to be really hard. It's going to be 3 whole lines. We're going to say string s is equal to get first, remove first, return s. Wow, so hard. That's the stack. This is all of stack. That right there is all that stack is. This is the only thing a stack is. It's super simple. It's a really easy data structure, but it's very useful. There's uses of stack go all over the place, but remember, all of stack is O of 1. You can see this is O of 1 because all that push does is it adds s. Now when we add s, what happens? Well, we are just setting our head to s, right? It's going to be O of 1. So this is an O of 1 method. Peek. What does peek do? It just does get first. Well, get first is O of 1. And what does pop do? It gets first, O of 1, and it removes first. Remove first also being O of 1. Yeah, so it's basically all O of 1. That's why stacks are super fast at growing and shrinking and letting you kind of pop through them. So a stack can go really quickly because it's O of 1 to pile stuff on. Boom. Boom. Right? O of 1. It's O of 1 to take stuff off. Very easy. That's the stack. That's why it's useful, and you'll see a ton of uses for it later on in the class. But the important part is that it's fast and it's easy to implement. But there are some things that are bad about our linked list. And the first thing that's bad about our linked list is it's not doubly linked, and that means that going from the end to the start is much slower than the start to the end, right? And think about this. In our linked list, what happens if we want to go in the reverse order? If instead of going from head to the end, we start from the end to the tail, right? Let's say that instead of going remove first, get first, we're going to get last. So we're going to get at L dot size, right? So it's going to take forever, right? Because every time we call get, we're going to have to go through the end, and then we're going to have to go all the way out to the end. Do you see how it's going to take forever to get to the last element of our list like this? Because to get to the last element, we have to get to all the way through. We have to use int I, and we have to go through the entire list to get to that element. So that takes forever. That takes super long, right? And just to see the end of the list, just to get to the last element, it takes O of n. That's terrible. What can we do for this? Well, we can add a tail and keep it singly linked, or we can add a tail and upgrade it to a doubly linked list. So how much time do we have? We have 19 minutes. So we could do a doubly linked list, or we can get into the tail. But first, I'm just going to make it a singly linked list with a tail. Right? So we're going to say private node tail, and we have to update our methods a little bit. So now we have to start head is null and tail is null. If head is null, we can say head is a new node s, tail is equal to head, because there's only one. This is a size 1 situation. And in the other cases, what do we have to do? Well, we don't actually have to change anything about this, because here our tail just kind of gets pushed backwards gradually, right? So let's make sure this works. Let's run it, but also let's add a getLast method. So public string getLast. Return tail, right? Tail.payload. Now, our remove method also needs to have it. So if head is not null, node temp equals head.next. Head.next is null. Head equals temp. All right. And now we're going to just say like, well, do we have to do anything with tail here? Well, our tail will always be the last one at the list, but our tail will be set back to our head. Well, our tail needs to be set back to our head if we're removing our last element. So, well, actually, let's see it. I think it could actually be fine like this. I usually do a doubly linked list when I have my tail, so I'm going to make completely sure of that later. But this should be mostly working, except this may be sus with the tail, but I'm too lazy to change it right now. So this may be sus with tail, but we are changing it soon, so no problem. Now we'll try it. So let's use our debugger. Let's see what happens to our list of links now that we have a tail, and now that getLast is also O of 1. We can go through, we can create our list of links, we can add, we can add, we can add. Now if we look at our list of links, we have our head, which is 807, it's a me. Next is world, next is hello, and our tail is hello, right? So our tail is our last element, our head is it's a me, and then 808 is our tail. So hopefully makes sense. Now as we remove, let's see if our remove method is proper. Our tail is hello, we remove, and no, we got a null pointer exception. So what's wrong here? Cannot read payload because cur is null, where here, cur.payload, why is cur null? Probably because our size wasn't properly updated somewhere. Did remove change our size? No, it didn't. Size minus minus. Classic mistake, always make that one. So now we rerun again. And let's see if our tail is properly maintained in our remove. And then we'll get into why the tail is useful for the queue. And then we can upgrade our list to doubly linked and upgrade our list to generic. And after that, we can use it for snake. So we're going to remove it. Oh, and this is probably silly with L.size anyways. We probably want to do L.size minus 1. Because indices should be smaller than size. Hello, 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 until eventually hello is removed. That's strange. Oh yeah, because we're removing first still. So this is probably a silly thing to do. We're just printing the last thing until the last thing is gone. Let's just do L.get0 to do a proper reading of it. And hit it with the debugger. and go through. So boom, 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 boom. Okay, so here's our list. We've got our head, we've got our tail, we've got our next, we've got our next. We can watch it. Now as we remove first and print first, boom. Gradually, now our head and our tail are the same. Now we're removing our first element, base case. And now we still have a tail. So what do we need to change? Well, if head.next is null, head equals null, tail equals null. Or maybe even better, if head, if head.next is null, head equals null, tail equals null. Now we can take care of our tail, and now we're good. Now, we can do a queue. So why did we need this for a queue? Well, if we look at our slides, our queue is able to actually access, and we'll get to doubly linked in a second, hold on. Our queue is actually able to access things from the end. So if we look at queue again, we can see that our queue is the same as stack, except it removes from the opposite end of the start. And we want both of these to be O of 1. Yeah, I will be posting the code afterwards. This is just so we can get the concept completely down pat. So our queue is going to remove from the opposite end that it adds from. So what do we do with this? Well, we have to be able to remove and add from both ends in O of 1. That's why we needed our tail. So let's get that going. To have a queue, we just go a new class, queue, and we will say extends list of links, and we're going to add our methods. So it's going to be public string dq, public void enqueue, and it's going to be public string peak. So which end are we going to be removing from, and which one are we going to be adding from? I'd say we should remove first, which means we also get first. So get first. Enqueue will remove first, or enqueue will add last. So we don't have an add last method yet, but we're going to need it. So add last s enqueue string s, and now we need a dequeue method, which will be the same as pop. Get first, remove first, bam. Return get first. So now we just need our add last method. Let's create it. Public void add last string s. Now add last is going to say basically same stuff for some of it, but the else statement will be different. So instead of saying added next equals head, we're going to say added dot next equals null, and tail dot next equals added. Now what this is going to do is it's going to add this one after our tail, and then we can say tail equals added. Right, so what does this do? This says tail.next is added, added tail equals added. This sets the pointer of the tail to our new one, and it adds our other one to the list. So now we can make a little bit of a stack and a queue demo. So why do we have a stack and a queue? Well, let's actually use our queue here. We'll say public static void main string args. We're going to say string test equals new string, bam, hello world stack queue. Now we're going to say, do a couple things. We're going to say for string s in test, we're going to say, oh, we also want to create these first. So q is equal to new q, stack s is equal to new stack, and we're going to say for every string string in the test, we're going to say q dot enqueue str s dot add, or I guess s dot push str, and now we're going to say while, or I guess, yeah, while exclamation mark q dot size or while q.size is not 0, and stack.size is not 0, 0, we will system dot out dot println s dot pop plus q dot dq. Now we can see kind of how the stack and our queue differ. So we're going to fill our queue and our stack in the same way, and then we are going to empty out our stack and our queue. Did we run queue.java? No, we didn't. We have to run this one. So this is why our stack and our queue are different. Can we see how the outputs differ between stack and queue here? In fact, I'm going to print them out right here. System.println. So look at the output here, and can you guys tell me what's the difference here between the output of the stack and the output of the queue? So stack and queue here, what's the pattern here? What do we see? These are having them accessed in the same order, but what's going on here? Well, one is the reverse of the order of the other, because the order of the input, if I make the same print line here, so if I stack and I queue, and then instead of popping and dequeuing, I peek. Peek will not remove it, it'll just look. So peek s.peek plus q.peek. Okay, so we've got our adding and we've got our removing. So when we add, oh, it shouldn't be hello, 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 because the peek, well, this actually tells us something useful too, but maybe instead of that we can print line str and str. So do we see how the queue and the stack are backwards of each other, right? Like they output in the opposite order that they add. This is our demo of how things are added and removed from the stack and the queue. They're added in this order. Hello, world, stack, queue. The stack goes queue, stack, hello, world, hello in opposite order, and the queue does it in the same order they came in. Does that make sense? Yes. 1, 2, 3. Now they can be like very much tracked, just so everybody can see the order that these operate in. And we might get to doubly linked to the list today, we might not depending on time, but I want to give you guys a practical example of stack and queue. So keeping in mind this order, can we modify our snake to be more efficient than using the array, using a stack and a queue? So in our snake, or I guess our, where is it called, our game, we have a snake, and if we have a snake class, we have this array of cells called snake. Now, what do we need to do with this array of cells? Well, when we eat something, we need to grow it by 1, and we need to add that thing on. So we basically need to add another thing to the snake. And when it goes forward, we need to basically get rid of the last thing, and then add another thing to the end. So we shift it over by 1, we remove the last element, and we add the first element. Like we add a new element here. Here we do nothing because it's dead. So is there any way we could use a stack for this, or a queue for this, or a linked list? Well, here, like this. Is there some data structure that we just learned about that we could use to make this snake more efficient than having to use a for loop?
Couldn't using the stack and queue methods, you could just add last, like you could just add one, like the way the snake eats something, as opposed to having to iterate through the length of its snake and then add.
Exactly, yeah. So that could be a more efficient method, and I think a queue would be good for this. But now we're going to run into a problem. Our queue holds strings. It doesn't hold cells. So do we want to change this to cell, or is there another solution that could be useful? Well, this is actually where generics come in. So here is going to be a bit of sorcery that you guys probably haven't seen before. It's called a generic. We put the triangle brackets here, and that's going to put a placeholder for a type. So here where we had string before, we're going to replace it with our placeholder. Everywhere there's string. Every instance of string will be replaced with one of these generic placeholders. Every string is now an E, right? So here we've got E. Here we've got all the E's, right? This one, it all looks fine. We don't actually do anything with that. This is an E. This is an E. Yeah, I will repeat it. Let me just get through it first. EE, add ES. Right, everything will become generic. Everything is now E. So again, our goal was to store cell instead of string. So to do that, we have to use what's called a generic. How do we get a generic? Well, our generic is specified here in our class. It's called like a generic. It's called a placeholder. It basically tells us that we can put whatever class we want inside of E. So before our code said that our nodes will contain specifically a string, and our list will contain only a string. Now we're saying that our nodes can contain any class, and we denote that any class with the letter E. So whenever we have an E, what we actually mean is any arbitrary class that we specify. Now we specify that class when we declare our list. So what does that mean? That means that here, when we have our, what's wrong with this? Node E, right? So when we declare our class, we're actually going to specify what type goes inside, and that's going to replace every time where we write the letter E with that class. So to get a code that's equivalent to our previous code, we actually have to properly do it. So here I have to do this one as well. We have to actually specify that it's going to be of type E. So I'll just keep converting this, and I'll show you. But at first, do you guys have any questions about how this whole thing operates? So are there any questions about how this kind of placeholder?
I'm not sure if I'm following. Can you repeat again? Sorry.
Okay, so the way that this works is instead of having our strings in our data structure, we say we can put any kind of object inside. And we need to know what kind of object it is to do stuff with it, right? So to do anything with our object, we need to be able to know what its type is. It's not like Python where we can just have unknown types. So what we have to do is we have to put a placeholder. Here I put the letter E as my placeholder, where E can be any class. So this here at the top actually reads as a stack of E's, like a stack of whatever class goes inside E. So the general rundown of it is like this. We have our data structure, which has these triangle brackets and a placeholder type inside, right? And when we instantiate it, do you guys see here with the ArrayList string thing here? Like inside the triangle brackets, we put what type of object goes inside. And that way we can say, instead of just we have an array list, we have an array list of strings, or we have an array list of ints. Do you see how that's useful, where we can specify what's in our list so that we know that when we read from our list, it's going to be a certain type? For that reason, we have these generics. This helps us to store lists of certain objects. So again, the syntax is like this. We have our data structure class name, and then we have the triangle brackets with a placeholder. And inside of our class, we can put whatever. Usually the letter E is pretty standard, so we put the letter E as the placeholder for whatever class might be there. So that's E is for like everything, basically. Any possible class can go inside there. And then when we instantiate our object in our code, we can say like array list of string, and by of string I mean the E is replaced with string, will be a new array list. And in that situation, every time we actually add something to our list, we actually say that it's going to be a string, right? Does that make sense? Like every place here where E is written is replaced with string if we make it a list of string. Every place here where E is written, it replaces with whatever type we want. Does it make sense? Our E is our type. So here, if I type Q of string, it's going to say this is a queue filled with strings. If I then say stack of string, we're saying it's a stack filled with strings, right? I know it's a bit of a new notation, but here, when I say queue string, or when I say, let's say, list of links string, what this is saying is this is going to be a list of links which is filled with string. So every E becomes a string, right? This here, this code says that every E, everything inside the triangle brackets, is replaced with string, right? Does it make sense?
Yeah, it does. Thank you.
Okay, cool. So again, the generic type means that every time we have the letter E inside here, every time we have this generic in the triangle brackets, we replace it with whatever we put in the triangle brackets on this side. So now that we have this power, we can see here our one queue and stack, it works in this situation where we have our queue and our stack with strings in it, but it can also work here, because now if it's a queue of cells, right, and then we can say snake is equal to new queue of cell, right, and now we just have to use this notation. So our get head will return, I guess, snake dot get first, right? So it's not like a very different notation, right? So now our new snake is going to be a, well, we don't need any of this anymore, right? Actually, right? What we can say is our, where is it? New snake. In the case that this cell is food, we have a cell C. We can say, where is it? C.setType dot snake, and then we can say snake dot enqueue C. Right, now that'll add that to the new like front of our snake, right? Now here it's going to be similar, except instead we also have to make the one at the end that was removed empty. So we can say here that cell removed is equal to snake dot dequeue, and now we can say remove dot set type empty. Moved dot set type empty. Now this, what should it do? It should do the exact same thing, but see how we reduced our lines of code? Here, what we did was we used our queue to enqueue and dequeue our various items. So when we enqueue, remember, it looks actually a lot like a snake when we enqueue and we dequeue, right? Let's take a look again. So in our queue, do you see how the plus and minus are at either end of this snake-like object? Right? So do you see how when we enqueue, we add something to the head of our snake, and when we dequeue, we remove the thing at the tail of the snake? Do you see how the way that the queue structure actually works is quite similar to how our snake game works? It's almost like the same data structure. Our queue is basically a snake. You can even think of every queue in Java as a snake, because the snake eats on one side, and then the other end gets removed. So as the snake moves along the board, it eats forward and it removes backwards. Eat, remove. That's just like a queue. Since it goes backwards like that, or it eats something, so it grows by one, then it removes by one, removes by one. Do you guys all see how a queue and a snake are kind of the same thing? Like, do you guys see the parallel here between queue and snake? Alright, so that's kind of an example of how our snake can work. Now, we're a little bit over time, so I don't know if I'm going to get to doubly linked lists today. They're kind of a minor thing. They just mean that the tail has always a pointer to the previous. Right? And what's going on here? Snake.get first. Oh yeah, if... Hold on 1 second. I just got to fix one little exception before I show you guys the final demo. So if head... Yeah, the code will be on my courses. No... Yeah, so the code will be on my courses. Now I'm going to try to run our snake again and see what exactly is happening. No, it doesn't like that head.snake.getHead is null. But snake has a head. Oh, I forgot to actually instantiate our snake. So back in our code, our snake game is not perfect yet because I forgot to actually, when we create our snake, we also have to add to our snake. So we have to say snake.enqueue C. Now we actually start off with a head because previously we didn't. Now we did. So now we have our snake and it moves around our board. Then it adds something to the queue. Right, well now it's a bit different because we can't draw as easily using the for loop. But yeah, something is off with it where it's eating, and it's eating a little bit differently. I think it's with the coordinate system. But otherwise, well, you guys get the point. The snake eats the same way a queue eats, so that is the snake and queue version of snake. And there's a little glitch with the snake being a little bit sideways, but we will figure it out. So are there any remaining questions for it, or anything you guys want to know? Again, sorry we didn't get to the doubly linked list today. It was a bit of a, content-filled section, but we did get through stack and queue, and they are reasonably fast. So any questions about any of it?
In the future, I was just wondering because of on Tuesday, and obviously I know you have a busy schedule and all, but it was really beneficial to have like part of the tutorial going over the quiz and explaining how like the hard quiz questions. So I don't know it's not really a
Yeah.
question, just feedback that like you showed me why I got a lot of things wrong, and I learned from that as much as I learned from seeing that.
Yeah, for sure. That is actually, we are planning to get that more of a format. The issue was actually getting our hands on more quiz questions, like, because a lot of them have to be reused in future years. So we actually have to have a lot more quiz questions prepared if we're going to go through them. But we are moving towards that and trying. It's actually a lot on the writing of the quiz questions to get enough going so that we can afford to give out like properly good answers and then still have quiz questions where people can't just go on YouTube and find old recordings to answer. But we are working on it, and we're definitely trying to make that this situation.
Thank you.
Yeah, for sure. All right, so that was the general stack and queue. If there's any related questions at all, happy to answer now. If you're watching the recording and you have any other questions, you're welcome to ask them on Piazza or otherwise. Oh, you're welcome to ask on Piazza or on my courses, or not my courses, or on office hours, or wherever you'd like to ask, and I'd be happy to answer your questions. Again, code should be posted same place as the recording, and all that. Last call for questions before we wrap up. Hey, so just for the recording, because I kind of forgot to in the live session, there's a little bit of an extra demo for how our snake uses our queue. So inside of our snake here, we have our eat method, and our eat method will either grow our snake or shrink our snake. And again, like we showed in the live, our queue works a lot like our snake because our queue has an add and a remove on opposite ends. So by using the queue, it's actually really simple to have our snake work. We'll eat from the end where we enqueue and dequeue. So I'm going to put breakpoints on food and empty, the cases where we actually move our snake. And now, as our snake moves, we start off, our snake has a queue as its body, and its head and its tail is the same node. Why is its head and its tail the same? Because look, its head and its tail are literally on the same square. Now, as we let our game progress, and our snake will eat and move upwards, our head and our tail are still always the same, but now if I make it like really likely that there's food. So let's just stop pausing, mute breakpoints, continue. We'll pause, and we'll make it so that the food is extremely likely. So food odds will be like 1 in 2, right? So now our snake will grow a lot, and we can actually watch as our snake will grow. Here that's unlucky, so we'll just move forward, mute our breakpoints, go. Okay, so now our snake is actually going to move around and we can watch it grow. So right now, our tail and our head are two different nodes, right? So our head.next is our tail. We can actually see that because our head is 2194 and its coordinates are 7, 6, and our tail has coordinates 7, 5. So head, tail. Now we go along. We'll go, let's say, next breakpoint, bam. It's eating empty. Oh, no, it died. Oops. Okay, so now it didn't die, it just didn't draw properly. Now we've eaten, we've moved forward by a few. Sorry, the game is weird with breakpoints, it's just not designed for it. But now that we've eaten a few, we can see our head should be at, well, here, up at the top, with a higher Y, right? And then our next has one that is, one below. Our next has one that's below that. Our next is below that. And then our final one is the tail, and our tail is also stored in our tail variable. Now this list is singly linked, so we can't go up from our tail to our head, but we can see how the tail and the head of the snake correspond exactly to the tail and the head of our queue, and how our snake is literally just a queue. Now if I mute my breakpoints, and I just rerun the app, we can actually see it. So, boom, 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 going through. Okay, I've eaten a bunch now, and I can now unmute my breakpoints. It'll pause the game in memory, and we'll see our head is here at coordinate 6, 3. Then as we move down, we have our tail at the very end, which is here at 10, 8. And then we can just follow our chain, and the head of the snake is the head of the list. Well, I guess maybe the head of the snail is the tail of the list. Either way, head and tail, add, remove, queue, it should be a pretty cool demo, hopefully, for you guys with the snake game. It's literally a one-to-one analogy, and it should make it pretty clear how stack and queue work. All right, next.